test, no? So today I'm gonna to give you a brief kind of information related to fracture toughness, fatigue, and creep. So tomorrow I will give you an example of questions that I will not give it to you, okay, in the notes, and you have to like prepare by yourself, okay? I'll just project the questions and then in the class and show you the way of doing. Yeah. All right. As we know, some of you did the FYP with Dr. Tay. So not many of you know about the fracture toughness. So when the word talking about the toughness, perhaps you will just know it, oh, this is something like very related to the toughness that you learn from the impact test, right? But anyway, it has no relation with the impact test that you did or you have done in the lab like 2 years ago. So this is a totally different kind of thing. So fracture toughness is actually to determine the resistance of the material or the composite, okay? And this is very common. This property is very common applied to metal and composite materials. So it's actually to determine how good is this material resist to the propagation of crack when there is crack happen in the composite. So meaning that there is already a failure, there is already a stress concentration happen in the composite or at the surface of the composite or inside the composite. Then we actually would like to prolong the composite by not having a severe failure when there is a failure there. So this is because sometimes it will always happen when most of the material when we use at a certain period of time, right? So then it will definitely, there is a stress concentration, there is a crack happen inside the composite or at the surface. No, so this is where the scientist or researcher would like to know how long this will be sustained. So same goes like our human. Myself, I actually has a sclerosis problem many years already, like more than 20 years or so. How can my bone being, like something like I have to, the material people and you yourself have to do some exercise or to prevent not the failure will not getting worse or something like this. Okay, so this is very different from the toughness that you learn. Okay, so this has been something already that is a crack happen. Right. So this one, so we crack on the surface of part would be likely to propagate. So propagate is getting longer. Example, there's a crack line, then the crack line would be getting longer and longer, and it could present a problem if you want the wheel to stay on a car. So sometimes it is some scenario, a certain how can I say, a certain time or situation, okay, we can't avoid, right? We can't avoid there's a crack already. So how we gonna to know that how long this crack will not be propagate? So it will be like this. The crack maybe is just a minor one. So it doesn't actually affect much of the performance of the material, no? Okay. If you have any question, please voice up, okay? or if I am too fast, also you please raise. Okay, so well, the shape of the crack. Okay, so the fracture toughness, one of the factor that will influence will influence the result or the fracture toughness. This one, the fracture. This is the crack geometry, the shape of the crack and geometry. Okay, the fracture toughness is Kc. Okay, so the geometry of the crack is also have a high influence to the result of the fracture toughness. So in this, I don't want to make you confused because there are many different types of geometry of cracks that it will be happen, and due to different geometry of the crack, then the equation you have to change. So for the time being, the questions will be just whether it is an external crack or internal crack. And we only learn in this class, we will only learn two geometry, although there are many in the following slide. No? Okay. Did I share this slide already with all of you? I just want to confirm. I forget. Did I share this slide with all of you in the e-learning? Yes or no? Yes. Okay. Thank you. Thank you, Anis. Okay. So good. So I have one more slide to share, then it's done. Okay. Critical value of blah, blah, blah. Okay. Yeah. Then we come to this, no? Grief. This is the scientist name, Professor Griffith. Okay, Griffith. He proposed that an existing crack will propagate when release of the elastic strain energy is at least equal to the energy required to create a new crack surface. So sometimes not sometimes, all the time, there is energy will happen. If there is a crack happen, the energy from two surfaces will be extra given, no? Something like this. Okay, this one actually is an internal crack. Okay, internal crack. So internal crack is very difficult for us to know, right? Use our naked eye to see the internal crack. So internal crack usually will be determined using the non-destructive test. So later on, next week, no, not this week. So next week, our last topic of learning will be what I can say will be a non-destructive test. So to know more, non-destructive test is actually more to let us know about the internal failure. That would be the main objective, no? Rather than those you have learned for the short performance test or the what you call it the destructive test. Okay, the destructive test is more on later on. Okay, later we talk about non-destructive. Okay, so and then following Professor Irwin, the family name Irwin, modified the Griffith theory by replacing the term. This is the yield strength. Okay, the potential strength energy release rate by this one, the G. So here it has called it replacing the potential strain, okay, then become the energy. So this is the what we call it, the stress, right? The stress, okay, stress strain. And then this is the what we call it, the size of the crack actually. Okay, so it will show that G is measurable and it can be related to the stress intensity factor, the K obtained from the sharp crack fracture toughness test. Well, you can, like example, I can't remember who is the one who will create the crack, right? To the material due to your FIP. So the critical condition to which the crack propagate to cause the global failure, and then it needs exceed the critical value of G when there's a energy, actually critical release rate, the energy is more than the crack energy, then of course the crack will propagate. So this one is common sense, right? The crack energy itself, and then you put more energy, of course it will crack faster. Okay, so talk about the stress intensity factor. Okay, this equation is important. Okay, this equation is important. Stress intensity factor, KIC, can be described as fracture toughness of material. So this KIC is fracture toughness under condition of, okay, brittle fracture, meaning that it is not what you call it, it is not a ductile fracture, it is a brittle fracture. Okay, why? When in the presence of sharp crack, meaning that the crack is quite sharp, something like the maybe like this, not this one. Okay, this is a sharp crack. Okay, not the round shape of crack, but it's like a needle like of the crack. Okay, under critical tensile loading, meaning that the load given is also very, very high. So under these three conditions, okay, under these three conditions, stress intensity factor, so where we can say the fracture toughness is the critical stress intensity factor, okay, in the mode 1 failure. So this one is the mode 1 failure. Okay, so AC is the critical crack length. This one, the crack length. Okay, this is the applied stress, APP applied stress, and alpha is the parameter dependent on the specimen and crack geometry. Okay, sometimes usually we'll use alpha as 1. Very easy. Okay, so how we actually determine the alpha? Okay, so under the critical, the stress under the critical condition. Okay, under the critical condition. So here you see, this is what I mean. You will feel very complicated, correct? So you'll feel very complicated, something like this. When we should put the alpha in what value? Okay, so I usually will give a question. Maybe I will give you in the question, I will give you the alpha. So this one is the internal crack, okay, with 2 times of the length. Okay, so then the alpha is equal to 1. This one. The parameter dependent on the specimen crack geometry. Okay, if the crack geometry is like this, round in shape, okay, and it is 2 times of the crack length, so this is alpha is equal to 1. So the question may give you what would be the alpha, okay, and then this one is the crack at the edge. Okay, so crack at the edge, like a sharp crack here, right? So this is 1.12, the geometry, unitless, no unit. Okay, like for this situation, is like a semicircle, not a thick one, but a thin semicircle. So it's 0.6, and then something like corner crack is 0.8, and then the semi-eclipse is 0.8 as well. Okay, so basically the question is this and this. Anyway, I will give you, remind me, I should give you the value of this alpha. Okay, right. So as the crack size increases, the failure stress increase. In addition, okay, we know you basically in the experiment, in the real experiment, when you would like to test the fracture toughness, usually people will create this one, the edge crack, because this is at the surface. This is on the surface of the material. It's easy for us to determine the crack, right? To create the crack. But the internal, like this is kind of difficult. This is kind of difficult, right? So maybe the corner crack and the edge is usually being used in the experiment to test the, what we call it, to test the fracture toughness. No, internal crack very difficult to create. How we gonna to create the internal crack? No, very difficult. So this is on the surface, the outer layer of the crack. Okay, so the composite material use a small diameter fiber to reduce the flaw. So in order to design, fiber reinforced composite, okay, so we usually will encourage the designer and the researchers to have a very small diameter of the fiber, so that it will actually to reduce or to against the propagation of the crack. Okay, so you see, if the length is shorter, right? The length is shorter, so the fracture toughness will be high. So we would like to have a high fracture toughness, right? So that's why it is advisable to have a, what we call it, a short, a very thin fiber, okay? Very thin diameter of the fiber. To achieve, it must be detected to prevent larger than a certain size. Okay, so we also can predict something like this. It is given, and then we need to determine what would be the crack length. So in order to get this fracture toughness of result, that it also possible, the question will ask, no? Okay, so in addition to surface crack, there are present accidentally material, the hole, the notch, the stress, blah, 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 blah. Okay, so in the recent development of technology, but I don't say it is recent, but it was done quite a long time ago. The researchers are working on this self-healing. You know, have you heard about self-healing? Self-healing. Anyone know about self-healing? Have you heard about self-healing? So self-healing is, can response please? I find some out like the silicone protector. We use epoxy usually. Yeah, regeneration. Yes. Okay. So good. Okay. So at least I got someone response to me. Usually if Jeff and Chaimela and Alif and Hanis and and well, okay. So so some of the researchers, when they find out there's a crack, right? So basically they will put the self-healing material to the crack to prevent the propagation of crack. Now, so thank you, Chairman and Jeff. So basically, the most commonly self-healing material is epoxy. There are many research has been done by using the epoxy as a self-healing material. Yeah, of course, it will have a different type of, we call it composite material together with this epoxy to be the self-healing agent. Yeah, so, okay. Thank you, Chaimei. Good try. Silicon is a protector that you already say is protector, right? So I'm not sure whether silicon also used for cell heating agent or not, but majority in the market is made from epoxy. Yeah, but I think silicon perhaps yes. Okay, I am not sure, but maybe yes. Maybe it can't be standalone. It will be together with epoxy. Yeah, because silicon is flexible, right? So that's one of the good candidate for cell healing. Okay. Well, this is how just now we mentioned about this, and then we try to produce polymer composite material with high ductility. So high ductility material. So the ductile material will have good elongation and good strength. Okay, so then the material should have better fracture toughness. Okay, so the thick and rigid material, usually they have a lower fracture toughness than the thin material. Anyway, to me, it does not necessarily the thin material which will have a high fracture toughness compared to thick. If the thin material is rigid, right? If the thin material is rigid, meaning that it is kind of fragile, also it will have a low fracture toughness, right? So example, the glass material, ceramic material, although it is thin, but it is still have a very low fracture toughness because it is rigid and fragile. Okay, so then we can increase the rate of application of the load reduces the fracture. Okay, somehow when we apply the load, I mean, you do the tensile test, right, to confirm the fracture toughness if there is a crack. So we quickly use the high speed of the load. So the toughness will be increased, the fracture toughness will be increased. So this is the research what have been done by a researcher. Also, they can play around the load, the speed of the load applied. So then you will see a different answer. Increase the temperature. Somehow it depends because increase the temperature. Example, like the polymer, it will be softened, right? So when temperature increase, majority of the polymers will be softened. So when they start to become they become softening, and then so they were more flexible. So elongation will high, and then so that the fracture toughness will increase because they become less rigid. They are soft. They are soft, right? So this is why it says when increase the temperature, but not that high. Okay, if that high also, the polymer chain will break. Then this is not what they call. This is not the ideal anymore. Okay. Small grain size. Okay, this is talk about the ceramic as well as the metal material. So ceramic metal material, if they produce in a, they have a smaller grain size, okay, or in short, in fiber also we have a small diameter of the fiber. So this is the same concept, no? But it applies to different material. So this is for ceramic and metal. So then it also will improve the fracture toughness. Okay. Oh, so do you want to watch the video on fracture toughness before I proceed to fatigue? Okay. Right, so let me check the fracture toughness. I just a very simple one, okay. Very simple, basic. Okay, let me try first. Kids. Okay, this one. Let
Hello,
me
welcome to Fracture Synopsis.
let me share this. This is actually fracture toughness is one of the topic of mechanics. You learn mechanics, right? Essentially, it is one of the topic about mechanics now. Let me share the screen, not the screen, but anyway, a window. Wait, kids, not. Okay. You can see this, right? Are you able to? Yeah, okay, you can see. Okay, good. So I'm gonna to like a project, gonna to play the video, okay?
We'll have a basic introduction to fracture mechanics. All right, so the first thing to address is, of course, what fracture mechanics is all about. And we'll remember from Synopsis 1 that fracture involves a crack of some length, the length of which increases upon loading. And fracture mechanics then is about understanding when that crack becomes critical. So when the crack gets to a sufficiently long length that the crack propagation goes from being stable to being unstable. And it turns out that we can describe fracture mechanics in its basic sense using this equation here. And this is something known as the stress intensity factor. Stress intensity factor. And that relates the stress and the crack length through this geometric factor here. Geometric factor, it's just a function of the sample size and the size of the crack. So this is a very useful equation for us. And it's, as I said, the basis for fracture mechanics. So I think to help understand the stress intensity factor, there's a great little statement in Hertzberg. This is an excellent book that he's written on fracture and deformation. Anyway, the statement is at the top of the slide there: stress is to strength as stress intensity factor is to fracture toughness. So let's just explore that. And of course, we've seen earlier in the course a stress strain curve. And on that stress strain curve, we identified a number of points, say the yield strength, okay, the ultimate tensile strength, and the fracture strength. And you remember that we called them strength values, and strength being a specific value of stress, okay, specific value of stress. So now we have the stress intensity factor K, and a specific value of that is the critical stress intensity factor. That is the stress intensity factor when the crack becomes critical. The crack has grown to a sufficient length that it is critical. That is the propagation is now going to become unstable. And more specifically, actually, we're going to look at the most common form of the stress intensity factor, of the critical stress intensity factor, the plane strain fracture toughness K1C. Okay, and the Roman numeral 1 there actually refers to mode 1, crack displacement. That's crack opening. Just out of interest, say here, crack 2, mode 2 is sliding, and mode 3 is referred to as tearing. But mode 1 is what we're going to be interested in. That's the most common form of crack displacement that we'll encounter. And so the K1C is the fracture toughness And remember that the fracture toughness is a specific value of stress intensity factor. So the last thing I'd like to just address is this clarification. We've covered a number of things here. Stress concentration factor, which was covered in the synopsis number 1, you'll remember was K sub T. That's the stress concentration factor at the crack tip. And that was just the ratio of the maximum stress at the tip of a elliptical crack, in our case, to the applied stress. Okay, so stress concentration factor, how much is the stress concentrated? And now we've also earlier in the year seen this property of the toughness, and we defined the toughness as the area under the stress strain curve up to fracture. Okay, so that's the toughness. That's essentially how much energy is involved in breaking and fracturing a sample. So it's, it's somewhat related, but it is a different term to this new term that we've just introduced, which was the critical stress intensity factor. So remember, the stress intensity factor, K, when it becomes critical, the crack grows, and we have a specific value of the stress intensity factor under the right conditions, which we call the K1C, and that's the fracture toughness. So it's important to realize that the fracture toughness is different from toughness to the area under the curve, and K1C is as well different from the stress concentration factor. So stress intensity factor, stress concentration factor, and toughness are related, but they are each unique, and it's important to appreciate that difference. So quickly, fracture mechanics is about understanding when a crack becomes critical. We have this relationship here for fracture mechanics. In fact, we saw that the stress intensity factor under specific conditions and when it becomes critical is known as the fracture toughness, and that is a material property. Okay. So that's a function of the material that you've chosen for the application. Stress is, of course, a function of the design or the application, and this is the crack size. And that could be something that you determine through non-destructive testing, or it could be a function of an element of the design or your processing conditions.
Okay, so this is just a common video.
And welcome to Fracture Synopsis 1. We'll cover an...
Okay, this is a common video. Okay, so and what can I say? Okay, and so it's kind of straightforward. Is what I have been shared to you. And then I have later, I'm not sure whether I have enough time to show the video, but anyway, later I'll show another video for the fracture toughness that is from one of the professor. He talk about this. Okay, so let me summarize a little bit. Okay, let me summarize a little bit. We didn't learn much. Okay, we didn't learn much. Okay. We didn't learn much for the fracture toughness. Okay, first, what happened? Okay, first, it is talk about this one. Okay, the fracture toughness at the critical. When you talk about stress intensity factor, that there are 3 conditions. In the video, it doesn't show. So 3 conditions happen. Only we can apply this equation. Okay, so when it's a brittle fracture, when it presents a sharp crack, no, and is under critical tensile loading, then we use this equation. So far, I also only teach you this equation. So the rest of the question I won't ask. Okay, so very easy. So only this equation. Okay, then at these 3 conditions, no. Okay, then we talk about basically we use these 2 equation, either is 1.12 or equal to 1. This is an internal crack, this is an external crack. Okay, so some of the factors how we're gonna to design a material in order to have have a high fracture toughness or better fracture toughness. For the fiber reinforced polymer composite, it will be always advised to have a small diameter of the fibers. Okay, so it will reduce the flaw, and we'll always have the materials, the composite with a ductile, uh, high, moderate or good ductile, good ductility, good elongation, and at the same time good tensile strength. If a material is very rigid, fragile, of course, the fracture toughness is low. So another way is during the test, no, or when we perform the test, the mechanical test, example like a tensile test, we can increase the rate of the test, the load. Okay, and then of course we also can increase a little bit of temperature, so the material will be more flexible. So the tensile or the fracture toughness will be high. And for the material of ceramic and metal, it would be good to produce those materials in a smaller grain size, so it will have a high resistance to fracture toughness. Okay, or high resistance to fracture and have a high value of fracture toughness. Okay, so now we move to fatigue. Okay, we move to fatigue. Fatigue is something like you heard about the fatigue, right? In our human body, sometimes we always talk about, oh, my body is fatigued. I feel tired, something like that, right? So, fatigue happens to the long performance test, meaning that it takes time to get the result. So, example, it may need 1 week, 1 month, several weeks to a month or to a year. Okay. It is a continuous type of test. We can perform the fatigue test using a tensile instrument, but that tensile instrument is a dynamic instrument, meaning that it it is moved like this, no, kids. This is the tensile machine, right? The tensile, you usually pull this up. This is our specimen hold. We hold it here, right? And then the tensile only keep pulling, go up, 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 and then it break, correct? So there another type of dynamic tensile test is pull, release, pull, release, pull, release. So this type of test, we call it a dynamic tensile test, and it is for the fatigue purpose, no? So you it will take some time. We always say the researchers they do like a 100 time up down up down up down 100 times, but that is not really called fatigue yet. Anyway, it depends on the materials, no? But if let's say the material can has a high fatigue strength, we call it, then that material is quite ductile. Yeah. So brittle material, usually we don't do this kind of test because brittle material, after maybe it can't be pulled down like this, right? When you pull a little bit, it already breaks. So we can't do the fatigue test on the very brittle material. So usually this type of test, the fatigue test or the fatigue property of the material will always be applied to those ductile material. Yeah, those ductile material. Metal, polymer composite, yeah, these two, or metal-based composite as well. So the result from the accumulation of very small amounts of deformation, yeah, normally elastic range. So you will see this elastic range. So this is for the ductile material. So the typical fatigue test result plot the failure stress versus the number of cycles. So in short, we call it S-N curve. Okay, so S-N curve. So it's like something like this. Okay, so you will see that the fatigue test result, the failure, the stress. Okay, we measure the stress still, okay, versus the number of cycles. Okay, stress versus number of cycles. So one like this, pull up one is considered one cycle, up, down, one cycle, up, down, one cycles like this, no? Okay. So fatigue is an important cause, and this one is no failure occur. There's no crack inside or outside the composite material. No, there's no crack. Now this is kind of like we assume that it is a perfect condition. Okay, the composite material is in its perfect condition. Okay, so fatigue is an important cause of failure in many cases because it can form crack that grow until they are large enough to cause a fracture toughness failure. But fatigue can result from cylindrical application, tension, and compression. So either we keep tension or compress many time like this. No? So in a different situation. So when we place our materials, our polymer composite material in a different situation. So when the situation happens, this is with a continuous kind of tension or continuous compression, bending or tension. So then it will for sure, it will, how can I say, it will encounter failure, but we don't know when. So that's why we have to determine is a fatigue strength. Yeah. Okay. So example, it happens to the aircraft, happens to this railroad, the railway road, it always suffer the fatigue, right? It keep continuous, the cycle keep happening, and many cycles, more than 1,000, 100 cycle, and thousands and 10,000s. Okay. So here you see we did a comparison. This is a stress over the cycles. Many, this is 1,000 cycle, 10,000, 100,000. Okay, 10 to a power 3 is 1,000. So 1,000 cycle to so many thousands. Okay, so we'll see after thousands of cycles, under the tension example, okay, you see the carbon epoxy polymer composite has the highest fatigue strength compared to all these type of metal. So metal will keep deteriorate after long cycles, right? So you'll see in here how superior or how good is this polymer-based composite. For sure, we need to have the carbon fiber is a long fiber with a narrow diameter, or we can say with a small diameter. So it only will happen like this, no? So this is carbon fiber. This is not glass fiber, kid. Okay, so you will see carbon fiber is very superior together with the epoxy, because we need something to protect the carbon fiber. So usually we use epoxy to glue them together to protect the carbon fiber. So very amazing. So this usually used for aircraft application, for bridge, construction, a big bridge, yeah, aircraft. So very superior type of material. It has a very high fatigue strength over a period of cycles to failure. Okay. So okay, so this is why. Okay. This is the explanation of the previous figure. Okay, so carbon fiber, inferior, blah blah blah, since high performance, and okay, so I have been explained to this. Okay, so fatigue failure in metal, fatigue of composite is considerably different. So instead of one discrete crack, it can have a many type of crack, maybe link up the cause of failure. So there are 5 major damage mechanisms. Okay, kids, this is important. Okay, so for a single material, the fatigue failure mechanism is quite easy. They just propagate slowly until it fails to a single material, right? But to polymer composite, what there are several damage. There are 5 major damage mechanisms happen. So it actually starts with the matrix. Okay, this is a picture. I have a picture, okay, like this. Okay, this picture is important. Okay, I highlight this picture is important. Okay, so it shows the 5 major mechanism of fatigue damage mechanism. Okay, so first it comes with the damage of the matrix first, because matrix is, you just imagine this one is epoxy with carbon fiber. Okay, so first, of course, the load start to transfer from the matrix first, right? Load transfer from matrix to fiber. So of course, the damage will start from matrix. So the matrix will crack. Okay, right? And then after that, it will go through this, we call it the interface of the matrix and carbon fiber will crack. It hasn't go to carbon fiber yet, okay? It has not go to carbon fiber yet. So you see here, okay? So, well, let's talk about this. Okay, for the first one, the first phase is the matrix will crack. Okay, this is very easy to understand and very easy for you to explain. And then when although the strength is lost, addition to the matrix crack open to the surface, and they can provide path moisture ingression. So when the matrix crack, then it open the path for whatever, like the moisture will can enter to the matrix, the sunlight. No, if we place things in outdoor area, right? Even though inside indoor we also have light. The light is also a UV, and we have fan. It's the angin, the wind, and then we have this humidity, other water molecules surrounding, so they will enter to this polymer crack punya zone, and then so it will actually accelerate the crack, no? Right. Then second phase, it will go to the fiber fracture. Okay. All right, let me check the fiber fracture. So 1A, so fiber fracture, it doesn't draw this one off. Fiber fracture only go to the crack coupling. Okay, so second phase 2 is the fiber fracture, crack coupling, and delamination. So it has, example, it consider 3 phases. Okay, then when the matrix fracture, all the matrix no have fracture. So then it starts to attack the fiber. Okay, but it start to attack the fiber, extensive crack. Okay, actually, be frank to you kids, to actually you know, not the fiber first, you know, actually is the matrix and then the interface. The interface between the fiber and interface between the matrix and fiber will start to fail, right? Because we learned interfacial addition is very important, right? So it is a barrier before the failure goes to the fiber. So it should be interfacial between the matrix and fiber start to fail. Then only it goes to this fiber fracture. Okay, only it goes to this fiber fracture. So yeah, okay, 0 degree fiber perpendicular to the matrix crack, and then the conventional. Okay, so only it goes to the fiber. Then the third, it goes to the fiber when the barrier between the fiber and matrix has gone. No barrier already. So the crack will directly pass extended to the fiber. Okay, carbon fiber. Then the carbon fiber totally fail. Okay, carbon fiber totally fail. Then, of course, delamination grow, and then the failure will totally, the whole composite will totally break into two. Okay, that is what I think you can write something like this. Okay, so this is the picture. Okay, so the crack coupling is the interfacial. So the delamination, and then the fiber break. So, okay, you can write a very short explanation or a brief explanation on this by drawing this figure. Then you will get full mark for the fatigue damage mechanism. How to explain the mechanism. Actually, the mechanism is quite simple, right? So I repeat, we start with the matrix. Okay, the matrix start to crack. So then the cracking continuous form until the coupling here. Okay, the interfacial between the polymer and the fiber, or okay, I can say fiber. Okay, so then when there's no protection anymore, the protector also being destroyed, then only the crack will start going to the carbon fiber. Okay, so carbon fiber slowly delaminate. Slowly, you call it delaminate because the fiber, usually it is laminated, right? It is being glued with the polymer matrix and with the protection of this coupling agent. So now no more. So when no more, delamination start occur, the carbon fiber become weaker, they become single together, they are not stick like this bunch, right? So, and then delamination happen, then of course, slowly the load applied to them, then the fiber will totally break. So, and failure occur. So you see the failure occur increase like this because they, at this point, okay, why it start and then propagate a bit, and then because the interaction addition between the carbon fiber and epoxy is very high because it used a very good coupling agent. So in order to against the failure, so they fight very hard. They fight very hard. Okay, this material fight very hard against the load applied. So that's why the fracture increase, the stress increase, and then it drops something like this. Okay. But anyway, this is the damage. So damage is the this is the damage is the optimum. Okay, not the optimum, but the highest damage become the highest damage. Slowly the damage increase become highest. Okay. Okay, so this is about the fatigue. I will give you the example of exercise, the question tomorrow when we have the physical class. Okay. So very fast, because without showing you the exercise, you cannot imagine. The exercise is about the tensile. It's about the tensile, but many cycles. Okay. Okay, so we move to, you want to take a rest before we go to the last one? or we can just proceed. Okay, so we'll say proceed. Okay, so I talk quite slow, right? Okay, now we proceed to creep. Okay, the last one. Creep is not about the load anymore. Creep is about uh, the length. We call it the dimensional stability or the length of the material. We observe the changes of the length when there is a load applied to them continuously. So this is a long performance test again, and creep usually used to determine the viscoelastic property of material. Guys and boys and girls, you still remember we learned this together in your second year on the subject of structure and polymer properties. There is one topic we learned about viscoelastic. Do you still remember? Sikit-sikit. Sikit-sikit. Yeah. Okay. So I want to ask, what this is from two words, just a little bit of revision. It is come from two words, right? Visco and elastic. Okay. So any one of you can explain just a very simple one. What is the meaning of viscoelastic? Okay, yeah. Okay, so what is the meaning of this? Viscoelastic. Most of the materials in the world, most, no? Majority of the material in the world uh, are, are viscoelastic. So what does that mean? Just a quick one, maybe can you answer me? Um, what is the meaning of viscose? Okay, having gel-like property, both viscous and elastic. Under viscous, okay, having a gel-like property. Hanya gel-like ke? Semua benda gel-like, okay? And then stable polymer behave both viscous and elastic under viscous liquid. Yum, 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 yum. Under viscous liquid. I just guess. Bagus tapa means that you not use Mr. Google to help, like it exhibit most flooring and spring-like property. Okay, very good. Okay, so in short, okay, thank you for answering, but I'm very happy you tried. No, very, very good. Thank you. So, in a simple way to say, material behave both solid and liquid at the same time. That is a layman definition. Materials behave in both solid and liquid at the same time. Very easy. Just use yourself as an example. You are a human being, correct? I am human being. So can you imagine your body? Your body has skin. You have blood, correct? So your skin is solid kind of feeling, correct? And your blood is a liquid inside. So you are viscoelastic material. Agree or not? Very easy to do like this, to explain in such a way. Agree or not agree? Agree or not agree? No, Jeff not agree. So you don't think your body is viscoelastic? Why? Why you not agree? Explain. No pula you agree. Okay, let us sell Islam. Okay. Not maybe. The answer is yes. Yes, correct. So it's not maybe. Science, we cannot, science is very straightforward. Okay, learning science is very straightforward. It's not learning arts. Recently I go to I met several friends. They are all the artists. Very funny. They love science and they love arts at the same time. Just made up the Lego. Okay, so it's something that very funny is that these science people also like arts now. So anyway, they brought me to the arts exhibition, something. Okay, done. So, and then, so to me, it seems like science is much easy to learn because science is yes or no, correct? Science has no maybe, no. No, this answer of maybe one, no, this answer of maybe, Isabel. Science is very straightforward. Yes is yes, no is no. So that is why when you talk to the people who learn science, you talk to the people who learn science, they are very kind of straightforward people. They won't tell you maybe like this, maybe like that. No. So those are very good in science, I mean, okay. And those people in arts, they have a lot of maybe, baby. But anyway, art is kind of very unpredictable. Art is something like sometimes it is full of imagination, right? And it is no totally wrong and no totally right things, no. So, but anyway, I have many friends, they love both. They are good in science and they also love arts. They are somehow quite special to me when you communicate with them. They have both characteristics. Okay, fine. So talk back to the science. Yes is yes, no is no. Okay, so just imagine ourselves. We human beings, we are viscoelastic material. We have two things in one. We have liquid and solid in one at this ambient situation. So it is not in a liquid situation at this ambient situation. So same goes to majority of the material. It's just maybe you can't imagine in a very straightforward way. Like example, all types of polymers, they are viscoelastic, all types. Okay, all types. Although you'll feel that they look like paper gel, right? They are solid. But sometimes they are a little bit gel-like, like what Isabel mentioned, or I can't remember who mentioned it. Okay, so they have both water, liquid, and solid behavior together. So then it comes to this what Sean's mentioned. It has this liquid, you have a Newtonian liquid, and then we have like a spring. The spring characteristic is the solid characteristic. So it has both, we call it Newton's law, right? You follow the spring is the Hooke's law and the Newton's law. Not the Newton's, correct? Is it Newton's law? Another law for liquid? Newtonian, okay, Newton's law, correct. Okay, so it have this material follows two laws, Newton's and Hooke's law. So you learn in your second year already. Then it goes to this. Yeah. So most of the materials is like this, except what I can say mercury. Okay, mercury is 100% viscous. So mercury is 100% liquid, no paper gel, no solid. So mercury is not viscoelastic material. Mercury is 100%, is nearly to liquid behavior. Okay, so it will not, the strength will be the same over the time. So this is the liquid type. It doesn't change the strength over the period of time. Sama aja, static, like this. Okay. Okay, so, well, this is, we talk about creep and stress relaxation. We learn this in our second year, okay? But in here, we will just want to learn about creep, okay? The elongation, okay, the elongation of the material will elongate at a period of time at the constant stress. So we just learn this in this subject. Okay, forget about this. We learn this. So this is a opposite, right? So opposite we have learned in the second year. So we continue this. Okay. So just now Sean mentioned about the spring. Maybe he already flipped through the flipped through these this slide, no? So we also learned this in your second year, right? So you have a spring with a dashboard. So spring is a solid behavior, dashboard is a liquid behavior. So combination of these become to a Maxwell element. Okay. Then we have another one is the void. There are two. So you see the arrangement of the dashboard and the spring is different. So this one is in a linear style, right? Okay, and this one is in like an opposite side. We call it the void element. So dashboard here, spring is here. Okay. Okay, so I only show these two because you have learned before. There is a complicated kind of a combination, right, of the spring and dashboard. When I show you in your second year, they are more complicated. But anyway, this is a mechanical model of like a viscoelastic material. Okay. Right. So for the creep, okay, for the creep, we actually measure the long-term application when the constant load applied to them and the elongation will happen. So elongation happen until it fail, but the load applied is very little. It's not like the load applied it's not like the load apply for the tensile test, fractional. You have a this one like very strong load applied to them. Keep pushing them like this, right? No. So for creep is very little bit, little bit, and then at a long period of time. Yeah, so strength versus time. So creep is a plastic deformation. So you learn about elastic and plastic deformation. You remember I also asked in the test, no? And I also emphasized in the class last week. So here the creep happened in the plastic region. So the plastic deformation resulting a long-term load, very long time, maybe several days, weeks to months. Okay. I have a student previously, she did this test, creep test before, for her master degree. Yeah, she did this test, and then well, she's kind of do kind of quite a good job because she did the research, is extending research of my PhD work, because I didn't do some of the long performance tests. So she did the long performance test. She did creep, fatigue, and yeah, these two major, because it would take a very long time to do it. So creep is affected by the temperature. So we can actually, as what I say, kids, I still remember the standard temperature, the test temperature in the world standard is how many degrees Celsius? You still remember? 25. Very good, honeys. Okay. So basically, people will still run the test in 25 degrees Celsius. But anyway, there are many researchers, they want to know the effect of the temperature, no? Because only constant load will apply. We can't change the load, okay? Because you do the creep, because you are focused on the elongation part, on the strength. So then the creep will actually, they will try to do it in a different temperature, high temperature, low temperature. Of course, at the low temperature, the material become rigid, brittle. So the elongation will be shorter, right? In common sense. And then if we increase the temperature, material become flexible, right? So more flexible. So the creep maybe will be higher, the elongation will higher. Yeah. 10% marked as a sample. Tests that extend beyond 10% life is preferred. Okay, tests that extend beyond 10% of the life expectancy. So somehow it is for us to predict, no, how long this material will elongate before it fail, something like this, no. And then the one that you did the fatigue is how much strength it can be before it fail, the strength in the long term, right? Okay, so measure the mass over the time, record the deformation. Okay, so this is a typical creep result. Okay, creep not in inch anymore, either in centimeter or millimeter. Okay, use SI unit. Okay, so creep is actually unitless because it is an elongation. So unitless. So mean centimeter per centimeter example. Okay, and then versus time. Okay. So typical creep graph is like this. This is a very obvious, this is a very easy and typical creep result. Some of them, you only get the straight line. It is actually means that the material is quite brittle. You don't get this secondary creep and then go to tertiary creep. Okay, so the creep result is usually measured here. The steady creep over a period of time. Okay, so the creep is, this is a tensile. Okay, at a constant load, we can keep push it out, but at a very low load, very low load. Okay, you keep push out, okay, like this. Then we calculate the elongation. The load is constant at a very low load. Okay, so here, student, this one is important. Okay, so just now I showed the fatigue is important, right? So for those who didn't attend the online class today, they tak tahu which one is important lah. Okay, so you know. Now, so only 20, I have 36, but always get 20 plus student. Okay, so you will see this figure is important. You may have to draw, okay, and to explain. So creep versus time. Okay, so the creep will increase and then it will steady for a while, not that dramatically increase, but it will increase a little bit, right? So this is a very huge, this is a very stiff kind of curve, no? And then it will steadily grow, the creep will increase steadily, and then it increase, then it go up. Okay, so now, first, it divided into 3 stages of the creep. First is a dislocation of the composite, the molecular or the composite to move move far away, so that it will elongate very fast, right? And second stage is the characterization of the location of the steady rate strain. So this is, we are more interested. This is the real creep. Okay. And third stage, necking happen, neck, and then it fail. Okay. So second stage is the creep. Okay, creep is one of the many types of material behavior that obeys the Archimedes relationship. So creep rate is the difference of time, the difference of strength versus the difference of time. How to get is actually, we need to plot a tangent here. Okay, we plot a tangent here, the strength divided by time. Tangent here, kids, tangent here, okay, like this steady state here, until here also, okay, the straight line over the straight line, okay, the tangent here, the difference of this creep deformation divided by difference of time. So your answer, the creep is S minus 1. The time maybe is hour or second, correct? But usually we will put hour. So it's hour minus 1. So the creep unit is hour minus 1. Hour minus 1, because it's divided by time. The strain is unitless. Okay, so tomorrow I will show the question and answer. Okay, so you pandai lah, you can keep it by yourself, but I will not share it out. You can take picture or whatever. Okay, so rupture time is the time required. Blah blah blah. Okay, so second stage is the creep. I want to emphasize, and this is important. This explanation also important. 3 stages of creep, and then second stage is the real creep. And then first stage is what happened, third stage is what happened. And you have to draw this. If you just do this like this, you will get full marks already. Very easy, no? Yeah, you don't need to give long answer. Okay. Now, I think this is my last, this is the question, right? Okay. Okay. I'm not sure whether I give it to you or not. Anyway, it's fine. Now, I come to this last slide, okay? Practical, we'll do tomorrow. Yes? Yes, Farayato, anything? You raise hand, anything? Ke tak ada? Ke you press wrongly? You mispress? Okay. Now, in general, these are the factors that will affect the mechanical properties, regardless is a short performance or long performance of the composite material, of the polymer composite material. Okay. First is the molecular weight of the polymer itself. Okay. And then second is molecular weight. This is the very basic, right? We start to learn this since you are in your first year. You learn how to calculate the molecular weight and all those things, no? Second is the cross-linking. Polymer, some are polymer cross-linked, some are not cross-linked. So cross-linking happen through the thermoset and elastomer. Okay, so for thermoplastic, this is the factors from the polymer itself, no? You see, many of the factors come from the polymers. But of course, you can divide the factors into 3. If you still remember, I asked question, factors into 3. So first is the factors of polymer itself, right? The molecular weight, the cross-linking, the crystallinity, the copolymerization, right? Then the second factor is the interfacial addition. Okay, so the interfacial addition of the polymer and the reinforcement of filler. The third one is the reinforcement itself. Okay, the fourth are all these. Okay, the environment. The fourth are the environment factor. Example, temperature. You can write temperature, no? Temperature, or the additives added. Okay, this is called plasticizer, is the additives. And then temperature is here, and then the rate of deformation, the rate of the load you apply, that is also depends, also will affect the mechanical properties, the pressure. Okay, so there are major, in short, if you are very good in explaining, you have four factors, four major. First come from the polymer itself, then you can write all the factors from polymer. Second is the factor of interfacial addition. Okay. Third is the factors of the filler or reinforcement itself. The geometry of the filler, you can write, right? The shape and size, geometry, shape, size. Then the fillers, aspect ratio, if it is fiber, the fiber's aspect ratio, something. Okay, so these are, and the amount of the filler that you add. Okay, then the last factor is the environmental factor. The environmental factor number 4, about the temperature, the composite of the temperature, right? The additives they added to the composite, and what else? Pressure, the rate of deformation. Yeah. Okay. So with this, I actually want to finish. Then tomorrow we look at the exercise, and then I may try. Then after the exercise, maybe I will explain a little bit of the non-destructive test. Yeah. Okay. Or do you want to view video again? Or I give a summary. You want view video? The summary is quite clear already, right? All these. Okay. You want to view me video or you want to rest? Cukup dah. Because I have 3 minutes more with you. You can choose. Video on this, they call it fracture toughness, still the fracture toughness. Or enough video. Okay, let me check now. Last one, huh? Okay, yeah. Actually, I want to show this fracture toughness. Anyway, let me check this. Basic. So this is the one.
鲜嫩牛肉，烟熏墨西哥辣椒酱，不容错过的精致风味。
Hey, do you know the dark secret of e-commerce sites like Shopee, Lazada, or Qoo10?
Okay, kids, I will show you this. I think one of the professors, just a short one, talk about this calculation so that tomorrow it will be easy for you. Just a very brief kind of calculation. Okay. Wow, it's very long then. What I want to show. Okay, wait.
QA here. So if you look at Callister, they have surface cracks which have a crack length of A, and then you can have internal cracks.
This one
internal cracks have a crack length or a length of 2A. So they're 2 times the showing like the energy was the last question definitely sees similar to the quiz.
So okay.
Okay, let's move on.
This
Here's
one.
some more equations and talking about fracture toughness. So in particular, so this graph is showing like the energy for if you have a crack and the crack was to grow, you need to give it some energy, and that energy is coming from the energy created by two new surfaces, right? So under tension, when you grow that crack, you're creating two new surfaces, two new interfaces. And then the counter to that is the potential relieved from the stress that's created on those, on those bonds. And so once you create that new interface, that stress is relieved. So that's a negative potential energy. But in any case, there's this equation called the Griffiths equation. It's very similar to, what we saw previously, and this is in the book as well. It's basically the same equation, just they took the surface energy, 2 times the surface energy, and replaced it with this critical strain. But it's related to this next problem, which I think is kind of fun.
Aircraft.
The airplane, the Havilland Comet, as Brush has talked about, ended up having a catastrophic failure in flight. And so the Comet fuselage made clad aluminum. Clad aluminum is unpainted aluminum. Okay, and the like American Airlines, if you're familiar with that kind of shiny silver clad native oxide, is 130 megapascals during flight. Calculate the critical crack length for catastrophic failure. All right, so we're using this equation this time to calculate for A sub C. So what size crack is necessary under these normal operating conditions to cause catastrophic failure?
Applied. So critical. He asked the student to do the exercise already.
So multiply by 1,000.
So this is the answer.
7 centimeters.
So you have to.
So the second part. So that's a really large crack, right? The last question, the hypothetical Boeing question, was millimeters, right? Pretty small, but still pretty big. This one is 7 centimeters. The second part of the question is, does this critical crack length explain the failure under
these are all the equations.
many cycles? You'll have a maximum stress load and a minimum maximum. So
example finish. Now this one is about the fatigue. Okay, so I want to show the fatigue. No, you see the graph is like this.
And some example problems from
sinusoidal. So time, this is the stress.
Cyclofatigue is kind of really interesting. So you can imagine you have a part.
So tomorrow we will learn about this in the example of the question.
But then over many cycles,
okay. So this is the fatigue SN curve. Okay. So this is only one cycle. Okay, one cycle. This one, only one cycle. Okay. Yeah. So you see only one cycle. This is only one cycle. Okay, up, one up, one down, one cycle. So it has many cycles actually. Yeah, over the time. So this is the fatigue. Typical fatigue graph, something like this, no?
Okay, you'll have maximum stress level. You can create and the steel having ways that will absorb energy. So this is the same Griffith equation.
Okay, so I want to show this anymore, or just like then would you want to have this video? I can put it in the e-learning, then you can learn it also by yourself by learning from this professor as well. Is it okay? You want to have this? Okay, no? Yeah. So I will put this video in the e-learning as well. Okay, let me oh, where is it? How come? Okay, then. Okay, I will just keep this one lecture. Okay. This one for you. This one for you. Okay, I made a note there already. Okay, so thank you very much. I'll see you tomorrow afternoon, not in the class. Okay, so see you tomorrow afternoon in the class, no? And next week we may have quiz on next week. Yeah, never mind. So I want to confirm because I have so many classes recently. Did I post the mini project already to you in the e-learning? Did I post the mini project? Yes, no? Okay, so you prepare. Okay, good. Then next week, after this week, early of next week, after I finish the
Right. So we're going to answer 7 centimeters.
I got this
I think that's correct.
Okay, so next week, okay, early of next week, I will post an assignment to you. Okay, so maybe the assignment also in a group. Okay, then you'll do it in a group work. Yeah. So after I teach you the NDT, only I will post assignment because the assignment is more related to non-destructive tests. Okay, so thank you, kids. I'll see you tomorrow. Okay. Yep. So bye bye. Enjoy your lunch. Okay. See ya. Okay.